That's great. Yeah, I just realized that.
I don't need to mute myself. Yeah. I just want to make sure your sound is being recorded. Yeah. All right. So I guess let's get started. So last lecture of the semester. So final project presentation. A reminder that while you finish the project, remember to fill in the course evaluation. Send me the proof for 5 more credits. So it will be very helpful for me to improve the course. So please do so. Right. So it will be closed sometime this week or next week, I think. So do it soon. Right. Yeah, and also we are going to do a presentation today, 15 minutes each team, so don't go long. And the project report is going to be due next Wednesday, 7 p.m. So I will use that to grade everything. Hopefully I can publish all the grades very soon. All right. So I guess the first group is the Pupper group. So take it away.
All right, good evening, everybody. We are the Pupper group. Let's get this rolling. So as an introduction, we are going to talk about our project, why it's important, and the methodology and approach we took. It seems to be lagging a little bit. Sorry, everybody. So we identified 4 goals, first of which is to integrate an Intel RealSense camera with Pupper in order to allow it to sense its environment. Implement an object detection algorithm so that Pupper can use the camera to detect a specific option or object rather. Implement a controller so that Pupper can autonomously move itself towards the detected object. And finally, we wanted to do all of this in ROS to the greatest extent possible to leverage some of the nice capabilities that ROS gives us. At a high level, our approach consisted of 3 phases. First, we needed to integrate the Intel camera with Pupper. So mounting it to Pupper and installing all of our supporting software. We actually ended up going with Ubuntu Server 2004, made it easier to install and work with ROS, as well as installing all the RealSense SDK stuff that we would need to fully integrate the camera. Next, we need to run an object detection model, which would give Pupper the ability to recognize an object such as a tennis ball. We did this by developing a custom ROS package using PyTorch and Ultralytics Yellow V5 as our model to run inference on RGB and depth images from the camera. Go into a little more detail on that in later slides. This node would publish any detections to a Pupper control node, which is our 3rd phase of our approach, developing a ROS package to do that. It would subscribe to the object detections, determine distance and relative direction to the object, and then craft a specific movement command to have Pupper approach the object. This is a very high level overview of our architecture. This bottom big block right here represents the Raspberry Pi that's on board Pupper. We installed ROS Noetic on it and it runs 2 ROS nodes. The first one's a Pupper RGB publisher, which takes the input from the Intel RealSense camera and then sends the RGB and depth frames to a Pupper object detection node. This runs inference on those frames, and then when it finds something of interest, such as a tennis ball, it publishes that detection to our Pupper controller node, which then crafts a command and sends it to the Teensy motor controller. Originally, we were trying to do all of this on the Raspberry Pi that's on board Pupper, as we'll discuss in a little more detail later. That wasn't computationally feasible, so we offloaded a Pupper object detection to a different machine, in this case, a VM running Ubuntu on Jared's laptop, which worked out pretty well. So I'll let Jared talk a little bit about the high-level ROS architecture.
So yeah, basically there was originally we were using the Intel RealSense ROS packages to publish RGB data, but for some reason it didn't like some of the configurations I was trying to give it, such as reducing the camera resolution, increasing frame rate. So I ended up just developing my own ROS node that drove the RealSense camera directly, and then published RGB images, depth images to whoever wanted it. That ended up in VM that was running the Pupper object detection node, and that basically runs the YOLO 5 model, pulls out the bounding boxes and calculates the depth to the center of that bounding box using the depth information. Bundles all that up into a detection message, which makes its way back to the Pupper controller. And then at that point, the Pupper controller can set its goal and then figure out the motor commands to get there. There were some software engineering challenges in implementing all of this. So this is the loose architecture of what that object detection node actually looked like. The biggest problem was that running the inference on a VM with only a CPU was painfully slow. And I implemented a kind of a dual thread architecture because that if the inference thread was slowing down the RGB frames coming in, which was essentially introducing a large time lag. So the detections were originally being detected a couple seconds in the past, and that lag increased as time went on. So essentially, we ended up having one thread just subscribing to callbacks and setting the RGB in depth frames, and then one thread that was pulling those frames and running inference on it, and then publishing detections.
So Larry, can you talk a little bit about our object detection model?
Yeah, so as we know, the popper doesn't come with any camera, any LiDAR. So one part of the project was having a camera, getting the image and detect an object of interest. Okay? So talking about object detection, one of the best model out there is the YOLO, the V8. Okay, but we are using YOLO V5 in our project. Although YOLO V8 is much faster, but YOLO V5 is more easy to use, right? So we pick YOLO V5 and we train. It is a pre-trained model that can detect a lot of objects, like I guess more than thousands of objects. 100, yeah. So we train it on a ball, right? And we get that data set of tennis ball, as you see, very easily from the Robot Flow API database, the tennis ball. So this is in development environment. So as output, we have the previous model, like you can see, the inference speed is 5 milliseconds. And it can do inference and detect different objects, like you see, sport ball, orange, apple, chair, things like that. And our model, the fine-tuned one, is able to detect tennis ball, right? That's the second result that you can see. And the inference is much faster in development environment, okay? But surprisingly, when we try to use it on the popper or on our production, so the base model was much faster, and that's why and it cannot run on the popper because of the Raspberry Pi performance limitation. So we had to offload that to a computer so we can have a good performance in terms of detection. And the popper would send the image, and we'll do the inference, offload the inference, and send back the position of that ball if detected, right? Next.
So let's talk a little bit about the popper controller.
So this diagram basically represents the popper controller, which was already on the popper before we introduced any ROS to it. It had the blue diagram basically is like the main loop, which got the inputs from this joystick interface, and then published the commands to sent the commands to the controller, which then interacted with the hardware interface. So we then replaced
I'll just let it do. Yeah.
we then replaced this entire one robot.py with the popper controller ROS node. So we made a custom 1.py, which was called popper controller.py, and then we made a custom controller as well. It's called follow controller, which is basically the brain of the automation. And then this follow controller just simply calls a supercontroller, which was already there, and that takes care of the hardware interface. Just use the existing hardware interface. We're not using the joystick at all. It's completely automated from start to finish.
Sure.
So in trying to figure out how to actually go forward, and especially returning, we we heavily use the simulator because we can get the exact outputs without any lag, and we can really mess around with buffer without any damages to the real buffer. So we use the simulator to develop the buffer control, to develop that like follow controller and buffer controller, which I showed in the previous slide. And we also developed the algorithm which calculates the yaw from the camera pixels.
Cool. Thank you, Saad. So we'll go over some selected highlights of our mini challenges. First of which being we broke buffer a couple times actually. The front left and right hip brackets split apart on separate occasions, but fortunately we were able to find the STLs of those parts and print out replacements. So we were able to do a good repair and get it back in action pretty quickly. And I printed out some spares for whoever inherits this next. They both failed in the same way, so I imagine that's just kind of a weak spot in the design. So, but we were able to quickly overcome that. Next up, as we alluded to earlier, the Raspberry Pi 4 wasn't quite juiced up enough to be able to do everything we needed to do. When we first tried running just the camera and inference nodes on it, we were getting like 0.2 frames per second inference, which yeah, it's not great. So we were able to leverage RAWs, which gives us a nice distributed architecture to be able to offload just that one node onto some other machine. And that was surprisingly straightforward. So it was kind of a testament to the power of RAWs and its ability to let you do distributed computation like that. We did have some throughput issues with publishing the full size 640 by 480 images over RAWs, basically amounting to poor tracking performance. And we had some issues configuring it to run at a 320 by 240 frame rate. So Jared implemented another RAWs node to basically pre-process and publish these images using OpenCV to do some processing and then publish it. And we were able to achieve up to a 30 frames per second rate with that. So that's a pretty impressive gain right there. Primitive motor controls. Yeah, we struggled to kind of understand some of the behavior. We did have that abstraction layer of hardware interface where we're sending it commands and it's doing its thing. Where doing its thing was not very clearly defined in all cases. So we had a lot of instances where it just kind of like locked up or did very wacky, unexpected things. But as Saad pointed out, using the simulator allowed us to kind of like smooth that out and kind of test out our overall approach before taking it to the real hardware, which helped us overcome that. And then finally, as Jared alluded to earlier, running in VM meant we didn't have any actual like, GPU resources available. So that did give us a pretty big hit on our performance. But again, the simulator came in handy to let us try some of this stuff out without that performance penalty. So in summary, out of our 4 goals, we accomplished all of them, I think. We were able to get the camera integrated, we were able to implement object detection, and we were able to get Pupper from start to finish to bring itself up, go find a tennis ball and approach it. And we did it all with RAWs. So without further ado, we have a live demo prepared over here. If everyone wants to come check it out. Or
Why don't you stop sharing screen so that
yeah, I can do it. Yep.
yeah, so that you can take over.
Yep.
So I also need to do this. It's working now?
Yeah.
Is it working now? Brenda, can you stop share? I want to see the IP address of the service. Oh, who is sharing this screen? Not me. Oh yeah, I just want to see the IP. Oh, okay. This is the IP, right?
I think you don't do the slideshow, or something that gives them away, you hit slideshow.
Oh, really? And then you
Or
want
maybe that's just in the browser.
Let
Like you do
me-
it here, it shows, but if you. No, okay, it's Microsoft Live.
All right, I guess you guys can still trying to make it work. While let me start to record start the Zoom. I want to make sure. Okay. Is it ready for demo?
Yeah.
Oh yeah, sure. Let's go look at demo first.
There's a video from this. Showing the thing.
And this is you, right? There we go. It's not. Yeah. Yeah, we didn't expect that, but I mean, we should have caught that, and that's part of the problem, like, there's so much sway in it, and you can't really get for this, you can enough to really. Really. It's a yeah, so in this case, we actually. Yeah, now we lost the goal. Once again, after the presentations, I guess. Let me start sharing this. Share screen. That's not one. And. All right, here we go.
Thanks. All right, so my project was like looking at a neuromorphic swarm behavior. So just as a quick recap of my project, I was looking to create useful or interesting swarm behaviors in 2D with simple robots using spiking neural networks. The long-term goal is to move to aerial domain via blimps, so efficiency is important, but this was just kind of like a baseline of whether these whether interesting behaviors could be kind of found at all and what those behaviors might be. The robots in the simulator are very simple with little space for sensors and hardware. It's modeled after the Epoch robot, which is pictured here. It basically has like this single binary camera that's a 0 or 1, and it doesn't have any means to like communicate or talk to anything. So very, very simple design, just these 2 wheels. So past work. So I mentioned this paper before in my previous presentations, discovery and exploration of novel swarm behaviors given limited robot capabilities. So this came out of University of Texas, Austin in the Air Force Research Lab. And it kind of formed the base of my research effort. So according to the paper, the researchers created controllers by evolving weights of simple networks using genetic algorithm. And the evolution focused on the novelty of the behavior. So there wasn't really like a performance metric. It was only the fitness function was entirely determined on whether the behaviors of the groups of robots were novel compared to the other controllers' behaviors. And the code base was released with the simulator that simulated basically the Epoch robot, a 2-wheel differential drive robot with a binary camera sensor. And your controller controlled the velocity of the left and the right wheel directly. But the kind of catch is the code base didn't actually have any weights evolving. It just had like this vector of values which were accessed via like the sensor via indexing. And I guess the theory is that this network exists. There is a set of weights that exists for this network that would create these output values, and they just don't bother actually evolving or using the network. I kind of thought that was like cheating, but so I did want to take just real fast, talk about neuromorphic networks a little bit. So they're meant to be closer to biological neural networks in current models because current models struggle to generalize. We talked about in the robotic learning lecture last week how if something's out of distribution, the network will just break. So neuromorphic networks are kind of the strategy to make things generalize better, and they're a lot more efficient to use. The main difference is that they operate in continuous time. So in a typical artificial neural network, you get an output, all your neurons fire every pass. But in a spiking neural network, they have these multiple time steps where they generate a single spike only if a threshold is released over the time steps. And these operate over binary spikes for both the input and usually for the output. Various techniques exist for this kind of encoding to get your discrete input values into these binary spike trains. And this encoding process and the continuous time nature of the networks makes the training very difficult. So, that's kind of why neuromorphic networks aren't as widespread. You might, if they're generalized better, if they're more efficient, why don't we use them instead of artificial neural networks? It's because training them and using the values they produce isn't as well understood. It's still an active area of research. So this is just like a diagram of the leaky integrate and fire neuron, which I was simulating for my project. So you can see it's like a very, very simple circuit. So it's very cheap to use and deploy. So I used the ARFL simulator for behavior discovery. I looked at 2 neuromorphic libraries, Lava, which is supported by Intel, which is what I looked at first. Ended up kind of wasting a lot of time on it. Eventually switched to SNN Torch, which had a lot better documentation. So that was like one of the big challenges of my project was like going in, this is my first time working with neuromorphic models. So going into Lava, which kind of has this bad documentation, I didn't know what I didn't know. So I had a really hard time training these networks. And I couldn't get the genetic algorithm to work at first. I think there's a bug in Lava for inference tasks, which was causing it, but there was also sort of an issue with the different parameters. So a neuromorphic network has more parameters than just the weights and biases that you see in an artificial neural network. And I had to tweak the genetic algorithm to support those. But that kind of, I didn't get the genetic algorithm actually working until later. And by later, I mean, it finished at 3 a.m. today. So I switched to a regression strategy in the meantime, focusing on the cyclic behavior that we wanted to evolve. So basically, I just had the two inputs, 0, 1, and I tried to train a network to output the correct controller outputs for the left and right wheel, which should be a very simple regression problem, but it actually took me kind of a long time to get it working. But once I did this larger experiment over these two kind of key hyperparameters, which is your network layer size, so your number of neurons, and the sequence size for the rate encoding. So those discrete inputs had to be turned into these continuous time trains, and the length of that is considered an important hyperparameter. And the behaviors I was looking at was cyclic pursuit. So basically the robots moving around in a circle, aggregation, clumping together, dispersal, spreading out over the available space, milling, which is kind of this repetitive movement around the space, wall following, and random. So my first was, this was kind of the big experiment over the hyperparameters, the top 10 results. So these all learned very good controllers. This one was the best one. It had a loss that was like basically 0. So it did a really good job, but it was larger. The hardware we have that can deploy and work on blimps effectively is basically an FPGA the size of a USB stick. And it can support 256 neurons. So all of these are viable, but of course, as I showed in the network diagram before, ARFL reported only using 4 neurons. So I ended up going with this one. So this one, which only had a hidden layer size of 2. So it's very small, has 5 total neurons, and it used a sequence size of 2. And it also did very well, had, it kind of gets lost in here, but it had a near 0 loss as well. So once I selected that controller because of its efficiency, and then I trained across for all the different behaviors that I was looking for. Interestingly, wall following was the hardest, which kind of makes sense when you see the controllers. But so these actual behaviors were discovered via the ARFL diagram strategy of using those behavior vectors and evolving them. And then I found kind of strong controllers that way, and then trained the spiky neural network via regression for these strong controllers. So these are the kind of the output result behaviors. So you have like the cyclic pursuit. So the robots basically begin in random positions spread out across the world. And then using just like that single binary camera, no means of communication, they form these useful behaviors as a swarm, using only 5 neurons. So I was able to get all of the behaviors working. The wall following one, so this is like, it moves very sluggishly around the wall. But this was the case for AFRL's results as well. There are kind of controllers for wall following, also often tended to just be like a very wide cyclic pursuit or very slow moving like this. It's also important to note that the AFRL's like novelty search experiment that they published, it doesn't actually produce all of these behaviors every time. So sometimes you might run it and you might just get like several milling or like a lot of variations of cyclic pursuit. Sometimes you won't see aggregation in that run. So like all these behaviors aren't necessarily guaranteed for each behavior run. So as I mentioned before, I did manage to get the genetic algorithm working. And these are SNN controllers that were found. So the first thing you probably notice is they're like way faster. I think they kind of extend past that -1 to 1 boundary that they're supposed to be adhering to. So on a real robot, they would just be at max speed, whereas in simulator, they just go incredibly fast. But I got some like interesting kind of novel behaviors that we don't see with the standard neural network experiment. So you have like this kind of cyclic pursuit that's sort of pulsing. You have this sort of like aggressive milling or kind of clumping and spreading out again, aggressive dispersal maybe. And this was like a very robust controller for milling around. So the robots are doing like a really good job of this sort of repetitive movement covering the entire space. And then the wall following controller is also like very strong, right? Like it's very good at finding the walls and moving around them, which was interesting. And these are the kind of respective cluster maps. This is the standard one. It does look a little more tightly clustered than the SNN controller, which appears to find like a lot wider types of varieties of behaviors. I also think that the K-Medoids clustering algorithm, it had 10 nodes picked, which was tuned to the standard strategy. So I think I could kind of tune that parameter, maybe get better clusters for that visualization. So a lot of what I learned was kind of in the neuromorphic domain, some early simulator struggles. But the future work, I want to kind of continue analysis and comparison of the new SNN behaviors that I discovered, kind of see how they vary more, how stable they are, and compare them more directly to the standard approach, and then move into the 3D space with blimps. And that is all.
Questions?
For the regression strategy, just means grid error. So between the output of the network, which, and for the neuromorphic case, I was basically doing what's called like the voltage output. So, and this diagram, you can kind of see like, so technically you're supposed to only be able to read the output spikes. But because I needed like these continuous values rather than just a discrete 0, 1, you do something where you kind of cheat and read like this voltage here directly, because that voltage is a continuous value. So you basically train your output of your network against the ideal controllers discovered by ARFL strategy of the vectors, the behavior controlled vectors.
So you do have like extra demonstration, okay? So you have the labels generated by AFRL.
Right. So it was kind of like this adaptation of the strategy called bootstrapping, because spiky neural networks are hard to train. A lot of times you will train an artificial neural network to kind of mimic the spiking network and then train the artificial neural network like you normally do, and then use that to train the spiking network, if that makes sense. So I had this artificial neural network behaviors discovered kind of in this classical approach. And then I used those discovered controllers to train the spiking neural network via regression. But that was because I couldn't get the genetic algorithm to work, but I did eventually get it to work. So these behaviors were discovered via the genetic algorithm of kind of exploring behavior novelty of the controller directly from the spiking neural network. And I got like kind of, I think, better, more robust behaviors, and kind of these new behaviors that were not discussed in the original paper.
More questions?
Why is the simulation environment you're using?
So it's a custom thing ARFL built. The base is Pygame, but they built in like their own physics for the differential drive robot.
Just for the sake of time, who wants to go next?
I can.
Okay, it's on Slack. Let me quickly download. Right.
Hello, everyone. So this is our project for CS685. So it's done by me, Muhammad and Amir. They provided much needed help and contribution like in the project and lot in the code. So this is like multimodal learning for social robot navigation. And whenever I, talk about this topic with my friends, there is like weird look among them. First of all, like the thing that robot and social behavior are two opposite end of the spectrum, right? And this is like how they react. So like a robot, socially aware, but why? Right? Why do robot needs to be socially aware? Right. So let's think of a situation that all the we have developed highly capable robots, but the social awareness is not infused into them, and they don't know anything about social awareness, right? And imagine a situation you have a robot at your home, and it has like all the access to the sensors, Google Home. It could open and read like all the sensors around your house. And you want to leave your house, you're in a hurry, and the robot wants to tell you some information. So it's like like it got into your way, you're in a hurry, and like it got into your way to your door, and like just to stop you and to give you the message. So that is very, very like unpolite or like irritating or annoyance kind of behavior. So this is like a single scenario where we want to, like one of the reasons that we want to infuse social awareness into robots. And these are kind of like the other scenario that I took from a paper that's last there in the reference. So like first thing is to respect personal space. And the second thing is approaching social behavior, like socially acceptable approaching behavior, right? When we talk in groups, we tend to form circles, right? Like, and imagine robot wants to come and talk to someone in that group. You don't want the robot to stay very far from the group, right? Or you don't want the robot to, enter into the middle of the circle and blocking everyone, right? So it needs to maintain that, social decorum of like, standing in a circle somehow. And then like you could think of like navigation, where all our work is focused on. And yeah, these are like a few more scenario where we want to know the robot about social awareness. Right. And the second answer that I get is like, why multimodal learning? Why not just go with unimodal? And I just grabbed this from like GPT-4, GPT-3 and GPT-4. And I got it from my friend who was working on a, CV project. So like, I think everybody knows that GPT-4 is trained on multimodal learning, right? It's like text, audios, text, signals, and I forgot. So there are some like that's multimodal, right? And like everybody who have worked in the industry, they will agree there is a lot of bad code people, right? But they always talk about good stuff. When you go to the video, they will talk about design architecture, design patterns, and like all that kind of good stuff. But it's a bad day at your code and you want to just complete the sprint and you write whatever. So there is a bad code. There's a lot of bad code out there. And when you see this, the unimodal chat GPT-3, the way of writing code, like, can you see, like you can see that it's like a child, right? And if you see the, like it calls the same function twice to do the same one. But GPT-4, you could think of like, it saw a lot of badly written code, but then it's like, it heard a lot of videos or like, I don't know, audios where people, talk about or brag about like how their design architecture is good and design pattern. So you can see the high level understanding of writing both are the same code. I couldn't, fit them into like a single slide, but you could see the key differences, right? It wrote like each and every functions first, and then it wrote a main function, then it called all the function. And this is kind of the high level behavior coming from the multimodal learning, I believe. This is just to tell you what multimodal could do, right? And the other background is like, if you're doing like navigation, why not just to image, use 2D images? Why to use 3D or like other multimodal sensor data instead of using just images when we could? So first of all is like, we want to use as much data as we can, useful data as we can to, to take informed decision, because neural networks are, performs better when they have more data, they take more informed decisions. So that is one key takeaway. And the second thing, mostly in navigation and like vision aspect, is when like people take this LiDAR data, 3D data, and then they project into a two-dimensional space in forms of bird's eye view image, and then there is also spherical projection. But the main problem with that is if you do 3D to 2D encoding and then solve the navigation problem, it may fail to encode a lot of geometrical structure that is inaccurately extracted into the bird's eye view images. And if you take this information and then just do your navigation, there is so much of accuracy that you could, or like informed decision that you could take, right? So this is and then like all the robots has like these days has cameras and LiDARs. So like this is just 2D semantic info, like this images capture semantic informations, and 3D like the LiDAR, all the point clouds has like XYZ coordinates, and they perfectly represent geometric information, though there's some noise. But yeah, so the thing is we could use this both 2D semantic information and 3D geometric information to fuse them together to solve our social navigation problem. Okay, so here's a bit about the representation. So when we like think of 2D, we think of pixels, and then like pixels has like RGB has 3 channels, and each pixel will have some values. But when you think of 3D and it's a 3-dimensional space, those pixels becomes cubes, like the voxels, and you could set the size of the cubes like 20 centimeter, 10 centimeter, whatever resolution you want to. But like essentially that is the representation. It's like it converts from just 2D grid, 2D grid to a 3D cubical grid based on your size of each voxels. And like on the right, there's just a a presentation of a sphere inside a voxel based coordinate system, right? That's how that it looks. And like I have covered this before, but I wanted to go this again. Like when you think of 3D representations, this is sparse. Even if you think of this room as a 3D structure, a lot of spaces in this room is empty except from this table, TV, and all the walls. So so this is a point mesh. So this is a LiDAR scan of a room. And if you could think of this whole space as a cube like this, the cube that I showed before. And like the cube has certain size, like 10 centimeters, 20 centimeters, and all these spaces are empty. Those cubes are like has 0 values. They don't have any values in it. And these cubes along the walls, they have some colors, these beds, walls, and like the floors, they have some values. So if you think of this whole room as a large cube, then you could think of like this volume, like a lot of this volume is empty space. So just to put this in perspective, so if you take a voxels of 20 centimeter at the length, the sparsity, like 78% of the space is empty. And if you could see, you lose a lot of this fine grained details of the scene. And if you go more high level, like more high resolution, like if I reduce the cube size to 2.5 centimeter voxels, 98% space is empty, right? So it's like just like, and you could think of, if you start convolving in this space, you will convolve basically zeros 98% of the time, which is like a waste of computation, right? And so, and just to put it into perspective, in a navigation scenario, I took this photo from the KT semantic segmentation dataset. So if you see, this is the car, and it has a LiDAR on top of it, and there is the LiDAR scan going on. I think there is a wall on the right side. And if you see all these cars, like as farther and further you go, the cars will receive less and less number of points, right? So you need to take a lot of points in this region to figure out this is a car, whereas a car like in this region will have a lot of points, reflecting back from it. So probably you don't need to look at a very big region to figure out it's a car, right? So this is how the inherent nature of light, it dispersed, like in a spherical manner and like completely outward. And like even the occlusion makes it worse. So if you see there's a car over here, so so this car over here is like, there is a very few points coming back from, right? Okay, so flip. Okay, so how we could handle this scenario is like, so currently we have this Cartesian coordinate system, right? Every point in the scene is represented in terms of XYZ coordinates. So if you think of all these points, like these are all the points, and each of them will have this XYZ coordinates, right? Like XYZ coordinates like this. The problem with the cubical system is like it does not captures the inherent nature of light. So if you look at this scenario, like the voxel based, so just want to go back. So if you see the voxel based representation, right, like the farther you go, the voxel size is fixed, right? And the number of points will fall in that voxel is going to be limited. But our problem is as we move, like go a lot of distance from the car, we need to look at bigger regions so that it will have more points in order to identify whether this a pedestrian or it's a car or a cyclist or whatever, right? So this is where the cylinder coordinates, comes into place. So basically what we do is we convert this Cartesian coordinate system to cylinder coordinate system. And the one thing that's very great about the cylinder coordinate system, as you move further, the voxel size increases, right? And it captures, so if you go further and further, a lot of points will fall in a single voxel. And in the end, it will like help in, understanding or inference if of the system, it like as it moves further and further away from the car, right? And the other problem is, as everything is sparse, we don't want to, compute, like do the traditional slide of kernels, because the 90, like as I showed you in the previous slide, 98% of the space is empty and basically zeros. And we don't want to convolve in those regions to make sense out of it. Rather, we want to use those walls and beds which has like non-zero value and had some existence, right? So this is where sparse tensors comes in. So you could think of this like a cube, and like if you see most of the cubes will have zero values, those are empty, and some cubes will have like some values that could correspond to the wall in the previous scene, or it could be a car or something, right? So this is like your dense representations. Like you take basically the 3D cube, like the NumPy or like that basic tensor representation. But in sparse tensor, you just keep the coordinate and their like feature, whatever you encode the feature as, right? So that reduces the computation to just 2%, because now you're not capturing 98% of the empty space, and you're able to store that 2% and do your inference based on that. In that way, you could take more and more, you could develop sensor that has a lot of points, and you could deal like in a lot of points without dealing with, the empty spaces and sparse spaces. And yeah, I have not gone in much into details of architecture, but I will, like there is a high level overview. But before that, I want to go want to tell everyone about the data set that we use. So it's a SCAND data set, stands for Socially Compliant Navigation Data Set. It's all the data is collected in UT Austin campus, and there are trajectories and like I think 4 human demonstrator navigated the robot around the campus in a socially compliant manner. And what we are trying to do is we are trying to use multimodal learning to predict the linear and angular velocity, which is like socially compliant, right? And this is I showed this architecture before, and this is the architecture. And there's a lot of things that we have changed since we read up the papers. Initially, we were thinking of using VGG. So think of this as 2 neural networks, like on top and on bottom. So the top neural networks takes images as input, and the bottom one takes the LiDAR point clouds that I showed you as input. So for the temporal variation, we are stacking up 4 images across the channel dimension and using a ResNet 18 backbone to get all the features. And for this, we are using sparse tensors, and we are using encoder, basically encoder architecture of a UNet sparse semantic segmentation, model. And we are just taking the encoder, not the upsampling part of it. And we will, and the middle layer is again another neural network, which takes, intermediate feature representation of these 2 LiDAR and image network, and it fuses them into a shared space, right? And then all of them are trying to predict, the same linear and angular velocities, and the laws are combined. Like I have not added the maths, but laws are combined, and then all of the networks will be trained jointly on the same task, right? So this is like a high level overview of the neural network architecture that we are using. So currently we have just done the image part, like on the top part, like we just were able to use ResNet 18. The bottom part for LiDAR is almost ready, but it's sort of very hard to work with point clouds. And I have some challenges in the last slide that we faced, but we have like coded the overall architecture, but there are some things, some bugs that needs to be, fixed before we could, train the whole network jointly. But this is like a very early, slim implemented of ResNet 18, which is the lowest version of ResNet 18. And you could see the loss is like going down in not many steps. The data is not, we took two ROSBEX file to, do this. It was not the entire scene, but yeah. And these are some of the challenges. So first of all is working with ROS is not easy. So probably everyone knows by this, knows this by now. And handling sparse tensors are hard because there is a very few limited libraries, and some of them are still in development. One is from TuSimple and another one is from, I think, NVIDIA. So those are the 2 libraries that you could rely on. And then the library that we are using also does not have a lot of documentation. You have to just read it and understand it. And then working with 2 neural networks is, there is a lot of overhead and like computational complexity. If you could think of a neural network that just works with images, you just download the pre-trained weights and then just give the input, like give the images to the model and then just do the whatever inference you want to do. But in here, you have to, write hooks to get the intermediate representation, and then you have to combine it, match the dimensionality, and then you further propagate to the next few layers, right? Yeah, it's done. So like those are the pieces that those are the papers that like really helped us in doing all the work. And yeah, that's it.
Well, the next team set up any questions for you can start in there in the Zoom. You can start. Yeah. Any questions for Rajan?
How the fusion representation is done, like how to know which features are more correlated?
Like we are giving those features to the intermediate the layer to figure out itself. So basically, all of the losses are optimized nicely. So hopefully it will learn some representation.
Yeah, now I'm on mute. Okay, so this is our motivation here. So as we know, the robot navigation is a very important direction, including like precision, positioning, mapping, and path planning. So we typically need to use sensors to obtain environment information and determine its own position in the environment. And we also need of map of by robots. And there are also some challenges here. So we need to typically perceive like complex environment. For example, we need to know unknown and dynamic pedestrian. We need to extract useful information. We need to generate a policy for autonomous navigation. So here is our objective. So typically we want to implement different navigation algorithms in different maps. And here we want to push the limit of each algorithm to find the best trade-off in terms of different variables, including like angular velocity, linear velocity, acceleration. And we also test the proposed algorithm in different maps, like those maps, some maps with the obstacles, some maps without obstacles. So we just want to see how our algorithm will work in different scenarios or different maps there. So this is our experiment setup. And for robot simulator here, we chose F110 simulator. F110 provides several different types of maps and scenarios in the simulation environment. And it can be used to test and verify the performance of the autonomous driving algorithm. So, and we also using Ackerman car. Ackerman car is a 4-wheel steering car. And this system determines the steering angle of the rear wheels through the steering angle of the front wheels. And you can maintain a stable driving track when turning. So actually here, we implement 4 kinds of different algorithms here, including the PID, wall follower, which we introduced last time, and follow gap, RT, and pure pursuit here. So we just want to compare those different algorithms performance in different maps, trying to see whether it can complete the task of like turning, go straight, like lots of things. So first is introduce what's the detail of those algorithm. First algorithm we implement here is the PID. So PID represents a proportional integral directivity wall follower. So a PID controller is a way to maintain certain parameters of system around specific set point. So you also using a variety of application requiring closed loop control. So it typically you use this formula as I illustrated last time we see here. So KP, KI, KT represent a proportion, integer, and derivative parameters, and which is contribute to the output here. And UT is using for steering angle, and ET is arrow turn, which represent difference between the set point and parameter we want to maintain around the point. And this kind of algorithm is a very common robot path planning algorithm in many use to make a robot drive along with walls or other obstacle. And for this algorithm, actually you need to base on the robot sensor data to control the robot's movement, so they can like maintain a certain distance or avoid collisions. And next algorithm we use here is the follow gap. So follow gap, the basic idea here is say if I near this lighter point and put a safety bubble around if it radiates R, and we set all points inside the bubble to distance 0 here, and all non-zero points are considered as free space. Then we find the maximum length sequence of consecutive non-zero among the free space point to find the maximum gap. Then we chose the furthest point in free space and say steering angle to avoid it. This is how we implement follow gap here. And the third algorithm we implement is RT. RT represents a rapidly exploring random tree. It's also a common like robot path planning algorithm. It aims to solve the path planning problem of robots in complex environment. And actually it's based on the method of random exploring tree structural construction. So actually we implement those in before the open project, the standard project, we implement this one. So we also use this in the open-ended projects. And the fourth algorithm we implement is a pure pursuit. It mainly used to control the robot to drive along the predetermined path and can track the path quickly and accurately. And how how we achieve this is we calculate the robot's control instruction based on a relationship between the robot's position and the waypoints. And we enable the robot to drive along the path and maintain a certain distance. We first generate the waypoints by localizing the vehicle in a design map using a particle filter, and we're recording the location with a waypoint logger. And we calculate a required steering angle to reach the desired point. So the next is a case analysis here. We have four kind of situations: go straight, turn, left, and others. So we apply the foreground on the street road and explore the movement of the car by changing speed information. And we chose the left street road for research here. So here we can see here, we have four kind of different algorithms, RT, wall follower, pure pursuit, follow gap here. This is a default setup here. We set the linear velocity at 1.5 meter per second. Angular velocity is 0.1 radiation per second, and the acceleration at 1 meter per second square. So we can observe the movement of the car is relatively stable under this speed for both of algorithms here. And we can see like shaking in the RT and following gap. RT has a like higher shaking level, and pure pursuit is the most stable algorithm. So then we change the parameters. We change the 2.2 meter per second. We want to see after we change the parameter, what kind of phenomenon or what kind of performance we will see in the different in those different algorithms here. So we compare with the previous speed. Let's see the car moves significantly faster, and the car shaking level of the RT algorithm is higher because actually RT needs to find the random point here. So if we increase the linear velocity, we will observe those shaking level will be like increase. And then for the pure pursuit algorithm, because it has a planar plus, so speed can be driven to the maximum and the moving speed is like significantly improved. And then we increase again to 4.3 meter. The car of the waterfall algorithm, it can still like maintain relatively stable, and the speed increase is not very obvious here. And the car speed of the pure pursuit algorithm is almost catching up with the speed of the marker. This is the maximum speed we now achieve is 6.6 meter per second. At this speed, like instability of the trolley, we can see it can be significantly improved here. And RT algorithm like start to catch up with the marker when the degree of shaking is high, and pure pursuit algorithm has exceed the speed of the marker. This is this is the maximum velocity we test here. So we see like after repetition experiment, we see like we found the speed higher than 8.3 will cause failure here because some of the algorithm, the car will hit the wall at the end of the straight road, which increases the risk of turning. And this is the actually what we illustrate when the car do the turning here. So the basic scenario we set here is 1.5 meter per second. The four algorithms both work and there's no failure after multiple attempts. And the turning parts of the RT is relatively short here. And this is when we increase the linear velocity and 2.2 meter per second. The overall speed is not much different from previous one. The follow gap algorithm almost hit the wall. When we increase to 4.3 meter per second, the pure pursuit algorithm shakes the list of three speeds, and the shaking level of RT is obvious here. You can see here, RT shaking is very obvious. And then when we still increase the speed here, the pure pursuit algorithm has a drift phenomenon we can see here. So, and the follow gap and the wall follow algorithm are relatively stable because the follow gap algorithm corner speed is significantly faster than the wall follower. And after increase the speed to 8.3 meters, the follow algorithm have high probability of crashing. So we can see both RT, wall follower, pure pursuit, and follow gap, those will be hit to the wall. So this is the analysis of the lap, which means the car is like driving around the map. So this is the basic SETA 1.5 meters. It seems that for street and the turn, it works well. And then we increased to 1.4 meters. This is also basic setup for 1.4 meters. For pure pursuit and follow gap, it works. At least for 2.2 meters, those works. And also this is for 4.3 meters. And 6.6 meter per second. So this is the summary of our results. So we can see from this result here, we try at least 4 kind of different algorithm, RT, follow gap. Oh, sorry, I didn't show here, which is the pure pursuit and then the PID here. So we can see follow gap outperforms than other. And pure pursuit has like draft proven since in. Sorry. Those bars represent the time, the finish whole step. For example, for street, how much time it consume, for turn, for lap. So x-axis represent the different velocity, 1.5 meter per second, 2.2 meter per second. So we can see the pure pursuit has draft provinces to track the preset point, and shaking level increase with the increment of the speed. And wall follower will take longer time because then follow gap because it needs achieve the obstacle of avoidance here. So it need take like much more time there. And we also deploy those 4 algorithms in different map here because we try to see when those 4 algorithms implement in different environment, different maps with obstacle, what would be the performance there. So our question here is if the map data is unknown to the car, we like randomly draw the car into a completely unfamiliar environment, what will happen? And we use the following 2 maps for testing. So first map here, we have obstacle here, and this one we have obstacle here and here. So we try to using RT pure pursuit. Actually, RT or pure pursuit is the pre-planning. So we need to know the map we need to know the map information, then those cars can work. So we can see in the new environment, new map here for RT and pure pursuit, it fails. But for the PID and follow-up gap here, because this one can learn the actually those 2 algorithms based on the like wall and gap there. So it can be used in any unknown environment here. So those 2 can be work and also like avoid the obstacle here. So we also put the PID, put a car in the map 2. We find in the for PID and wall follower, this first it works for this map, but for follow gap, it failed. So this is our conclusion, and we implement different autonomous algorithms for navigation, and we testing with different parameters in terms of linear velocity, angular velocity, and acceleration. And we understanding the behaviors of different algorithms and complete data analysis. And we test the proposed algorithm in different maps with or without obstacles. So that's all. Thank you. Yeah, we try to text what will be the maximum speed to pass all the corner and complete the racing.
How are you using this maximum acceleration in all your methods? For example, how are you using RT for this? How are you using RT to consider the maximum acceleration? So
I can say and I choose from 1 to 10 to set the speed, and I test that the highest speed is about 8.3 meter per second. So I think that's has so for 9 the car will has the problem maybe.
how do you, because you do have a maximum acceleration, how does your all the methods consider the maximum acceleration?
So basically here first for the acceleration here, we just can try to set different parameters in case of the linear speed there. But for if we want to increase the speed to a higher one, so we need to change the accelerometer. So it can be like in a shorter distance, we need to change the parameters of acceleration, then we can achieve the higher speed. So based on the linear speed, we can change the acceleration there.
So if you track if you times that, the difference won't be bigger than the acceleration.
So actually, we for measure the whole, I think the whole map there, we use the time step, just using the starting point and the end point here. Then because we have a linear speed there, so we can have those distance. Then we divide into this linear speed, then we can get acceleration there.
Recording. Okay. That's it. Sorry, 1 second. There we go. Okay. So yeah, so project speech-based parameter tuning. So just a very quick recap. Basically, our goal is to allow a human operator to communicate with the robot by giving it speech commands, and then those speech commands can update the parameters for the local motion planner. So, for example, you could say move slower, and it will dynamically update parameters associated with things such as velocity, acceleration, and then you can also give it absolute parameters. So if you want to set a parameter to a particular value, you can do that as well. So just a quick overview of the pipeline. So it'll accept speech input, and then that will be run through the parser to help us determine if it's absolute or relative parameter, how much to update it by, etc. And then that will be published to the parameter server where the motion planning parameters will be updated. So our approach, so first thing we had to do is we had to build a data set for our NLP model. So we use a BERT model. We made about 400 samples manually, and then we did some data augmentation to expand our data set. So when we augmented it, it actually helped increase our accuracy a little bit. So that was really helpful. And then the next thing we had to do is we actually made two nodes, two ROS nodes. So we made a publisher node. The publisher node will process the speech, and it'll basically wait for speech input. And then it will parse it into a output label to help us know which parameters we need to update. And it'll also use like regular expressions to help us figure out if it's an absolute parameter, say set the maximum velocity to 0.7, it'll help us get that amount. And then the next node we had to make was the subscriber node. So the subscriber node will take the label and the amount from the publisher node. It'll translate that into parameter updates, and then it will use ROSPy to send those parameter updates to the parameter server. Okay. So here's just a list of commands we have. So just basically go faster, and then if you wanted to change the parameters associated with, say, velocity, acceleration by a greater amount, you could do a command with label 1. So some capabilities. So yeah, natural language instruction. So the publisher node will wait for natural language instructions, and then it will dissect that and run it through our BERT model so that we can get the output label. And then they'll publish that to the subscriber node, where that will be translated into the set of parameter updates. So here's just some quick results here. So it can be done all in real time, and it will constantly be waiting for input. And as you can see, we just showed two different instructions here. So we wanted to set the maximum velocity parameter to 0.7, and that was the first command. So it sets it to 0.7, and then you have like a relative parameter, like go slower, and that'll update a variety of parameters. You can see there's maximum velocity, minimum velocity, acceleration limit, and so that'll correspond to like a set of parameters, and it will change it by a percentage. So it'll increase it by 20%, and then if you want to do like go way slower or like go much more slower, it'll be by 40%. So some things we learned while doing this. So we learned, how to create ROS nodes and packages, and how to interact with the parameter server, and that there's a lot of moving parts. Someone mentioned earlier that ROS is challenging to work with. We learned how to integrate the natural language model into the robotics space and use it for updating the local planner. And we learned that there's a lot of unexpected challenges and difficulties. So we were going to do a live demo, but the microphone is broken. It just fell on the floor. So we recorded a backup video, fortunately. So I will play the video, and then I'll just give some context to it, because obviously this is kind of like half recorded, half live. But basically we are running all the nodes. So we borrowed some of the Barn Challenge worlds, and we used the Jackal robot. And so the publisher is listening for speech input. And then, so you could give a command like set the maximum velocity, for example. And then we have it print out to the publisher node. So it received label 9 with amount is 220, which is kind of a high amount, but you probably would do a much lower amount. And then I think that might be, okay. Did you just do the one command in there? Yeah. Oh, okay. Okay, so we have. Yeah, this is a video. This isn't. Yeah, so what optimally would happen is you would be able to just speak, yeah, except the. Sure.
The last part of it is where it starts accelerating a bit.
You said 29? Yeah. Oops. Yeah, no, literally, I brought this microphone. Yeah, literally the microphone fell when I brought it to my lap, and then like it just like broke apart. Okay. Yeah, so apologies for that, but hopefully you get the idea at least from the video. Okay.
I've done the average frequency. So for example, in one sentence to 10 different sentences, but they have the same meaning. So for example, you can say like go faster or run faster. They mean the same. They mean the same. So we increase the data like 400 to 2,000. So what's the library? What's the library? Yeah. What's the library? It's the bird-based library. Yeah, use the Beam search. to generate more data.
Can I go? Okay. Hi, everyone. I'm Anuj, and this is simulation in Unity for high-speed off-road navigation. So basically, the primary goal was to create different terrains in Unity, and then try to implement physics on Unity so that we could generate data from it. But fortunately, I was able to do that before the midterm presentation, and I had to find a new goal for the project itself. So I decided on working on the data collection pipeline and transfer whatever I implemented on Unity to the real world, and report on how efficient the sim to real transfer was. So I wasn't able to play the videos last time, so I made sure I could play this. So this is one of the simulation that I showed in the proposal as well. This is the robot on the right, and then this is the image that the robot is getting from the camera it has on, and this is all the LiDAR point clouds that it has. So this is our Unity environment, and so what I wanted to do was to implement physics on the terrains. Obviously, I didn't do complex environment like this because this would take a lot of time, and I didn't want to spend a lot of time on that. But yeah, so what I did was create terrains with the physics in Unity, and then load the robots on those terrains, and then run scripts to run those robots in a replicable way, which was circles, and get the ground truth position of the robot and compare the results with other terrains. So again, I wasn't able to play this video on the presentation before. So basically, what I did was run a certain script on different terrains. So this is an icy terrain that I created with. It has low friction coefficient as compared to another terrain that I created, which was the grassy terrain. And the robot basically starts at the same position and goes around in circles so that I could trace the ground truth position of the robot and then compare it with another terrains. So this was the result, and you could see that the blue paths are the icy terrains, and then the red path are the red path is the grassy terrain for higher speed, and then the one on the bottom is for the lower speed. And we were able to replicate good like higher variability for icy terrains and then lower variability for the grassy terrains, and we were able to achieve that. So after this was done, we wanted to work on collecting the I could have gone like two separate ways. I could have either like made the physics better, but with what we had and what the results we got, it was already good enough. So we wanted to work on the data collection pipeline. So what the pipeline would look like is that we would get the information of the world state of where the robot was going using the onboard camera that was on the robot, and monitor the robot state, say YN, as the robot was going into the world state, and then execute some control inputs on the robot. That would be like a new V and omega while on the terrain, and then monitor the robot state as it came out of the world state. So this is what I wanted to collect from the simulation and then transfer it to the real life. So getting the image. So this is again, this is the previous icy terrain, and this is the image on top is the image that I could get from the robot's camera, and then the one on the bottom is the same image, but just a part of the image. So somewhere around here, and it has been transformed into a bird's eye view so that we can learn from it better. So the one on the right is the world state, the world that the robot is operating on. It's just going on zigzags, and this is the image, and this is the some part somewhere around here of the image that I got from them. So after this, I was able to transfer this into a robot as well. So in the picture, the one on the left is the complete image of the what I got from the robot's camera, and this is the robotic lab, and then this is some part of somewhere in here. My apologies because this is black and white, and I want to do it in RGB but I wasn't able to get it. And also the image on the right is stretched quite a bit because I wanted to fit it in like a symmetrical manner. So, but like this is basically the image, and it's getting some input from somewhere around here, and then it's transforming it into a bird's eye view. So after this, I was able to finish up until here. So I wanted to talk a little bit about the issues I faced in the sim to real transfer. So first of all, I couldn't get the robot working and I had to spend some time fixing the robot itself. And then I couldn't get the camera working. And which is why you saw the black and white image. I wanted to get the RGB images, but I had to work on making the camera working. And special thanks to Aniket for helping with that. And the image size published in the simulation and the robot were completely different. So I was actually able to do the bird's eye view first in the robot and then in the simulation. So it was actually the other way around. And I also could not get the IME of the robot to work. So I wanted to, so I could not do the whole data collection pipeline after that. So there was lots of issues regarding the IMU from the IMU device, including like broken packages in Linux to faulty SD cards and stuff like that. So there were a lot of headaches. So like I mentioned, the camera image is not RGB yet, and the GPS data is I still need to implement. I still need to integrate the GPS device on the robot itself, so that I can get the ground truth of the robot or on where it's at. And so I tried taking it outside, but I couldn't connect it to the Wi-Fi. So I wanted to do the bird's eye view of the terrain itself, but like the robot had to be connected to my laptop, and it wasn't in the same network. So I couldn't. I couldn't get that. So like this was also one of the issues that I kind of overlooked, and I took it for granted because it would not have been an issue in simulation, and it was an issue in the real world. So conclusions, like I had good success on the simulation front, but I had to spend lots of time working on the robot itself, and trivial things in simulations had like huge issues in the real world, and the inter-device communications are a headache. So the robot in itself, it has the box on top is a really powerful computer, and it has the camera and the LiDAR, and it has a GPS antenna, and then the 5G antenna, and then these things you will not have to worry about in the simulation, but like when you take it out to the real world, you have to take into account the networking issues and the communication between the devices and all that stuff, which are a headache. So yeah, that's it. Thank you. And this is the robot going around outside our engineering building, and I almost took out somebody's lunch.
So is the robot just like broken? Like you mentioned all the issues you had. Was it just
So it does work, like you can see. So right now I'm operating it with the joystick, but it doesn't like, I mean, we had to take it apart previously. That's why it was not ready to like go off the bat. So we had to fix we had to reflash the computer that was in the robot previously. So that's why it wasn't set it up to properly.
Want to go next?
I think I'm the second last.
Questions? You have 1 week to make.
Connect. I share from the Zoom.
Zero 0706.
So I'm going to talk about multi-agent cooperation using multi-agent reinforcement learning. So let me start with the background. Since we know that single agent means just the one agent in an environment with just one intelligence trying to achieve some goal or some task, and multiple agents means there are more agents involved in the environment to achieve some kind of collective goal. For example, like playing a football, or there could be, if we take the example from the natures, there are lots of multi-agent systems who have been working collectively and who have been doing their work in group, in a swarm, in a collective manner successfully in millions of years. If we see the examples of ant colony and the bee colony, they are one of the successful group of intelligent biological intelligence system in the nature. So nowadays, taking the inspiration from the environment, from the biology, there are lots of multi-agent systems that are being implemented. They are built and implemented in the real world. In terms, especially in case of in the field of robotics, like for example, drone delivery, UAV surveillance, autonomous cars, or let's say home robots. It is also very popular in this cybersecurity field and smart energy grid fields. So my main PhD research is currently now focused on multi-agent system, and I was inspired by the few questions to start my journey in this multi-agent system research. First motivation is how the collective intelligence work, like how the group of different individual intelligence being can work together collectively, and then what kind of cooperation and collaborations is possible between those different autonomous intelligent agents, and then how the cooperation and collaborations dynamics change in presence of adversity. These are the main three research motivation that inspired me to do this project and also my research. So I also, as I talked about my previous work on team coordination is state dependent cost. In this paper, we were able to find a mechanism or a model to find a shortest path for two agent system, but using by converting it as a single agent problem in terms of graphs. And then I want to make some improvements on this baseline work where I want to scale the number of nodes, number of agents, and implement single agent reinforcement learning, and then also hopefully implement multi-agent reinforcement learning. So I started my experiment with two sort of experiment. First, I started off with this grid wall based experiment, and then I later I tried on graph based experiment. I tried the first grid wall based experiment mainly because most of the resources available in the internet were just based on grid wall, and then there were like basically none or very few graph-based approach that were being used with the reinforcement learning. So in the grid-based world experiment, first I tried to use Q-learning with single agent in presence of obstacle and without obstacle. I created a simple grid like 5x5 kind of grid to learn the Q-learning. It was easy. And then I tried to work on independent Q-learning where I used two agents to learn independent policy. But the problem with the independent Q-learning was that the two agents were learning the policy individually, and there was no any kind of coordination behavior between the agents. Like IQL was basically not capturing this coordination, this cooperation behavior. And then I switch to a more complex approach, which uses deep queue network. And then I first started with a single agent, and then it worked flawlessly. But then when I added a two agent with the DQN, but then they also failed to learn this complex behavior between the two agents. So I realized I should go with another approach. But before that, I want to talk about briefly about Q learning and then this DQN and independent Q learning. As we have already studied in our previous class that what Q learning is, it is basically a model-free reinforcement learning approach where there is no model of the environment. So what agent does is it's try to do some actions, and based on that it explore the environment, and then based on the action it performs, the Q value will be calculated for that state, and then over time through multiple iterations it will learn which is the right actions or the optimal actions to increase the Q value for that state. And then for this Q learning, you basically use this dynamic programming approach, and we just need to do a lot of table lookup to improve the Q values in different throughout the iteration. And then in case of deep Q learning, it is the same thing, but it has one difference, that is it uses the state as an input only, and then it outputs the Q value action. So if there are like 4 possible action like east, west, north, south, then it will give the Q value with the which action performs the highest, which action will give the highest value. Based on that, we can select the Q value with the highest possible value given by the action, right? So what it does with the deep Q learning is it, in case there is the table number of table grows in Q learning, this can be significantly handled by the deep Q learning because it will learn this function approximation by itself. And then independent Q learning is basically the Q learning, but the different agents are learning the Q learning on by themselves individually. So it can be done sequentially or parallelly. It depends on how you apply that. So it's basically the same Q learning algorithm we studied in previously. So while I applied this, one thing I changed here while choosing a policy, I make sure that the agent also explore the environment. So I introduced this epsilon greedy approach, and then where 50% of the time the agent will explore the environment, and 50% of the time it will use the policy generated from the maximum Q value from the table lookup. But while I was able to do grid world based experiment, I realized few limitation in the grid world, like Q learning obviously does work flawlessly with and without the obstacles, but the independent Q learning, it doesn't learn the coordination behavior, and same with the DQN, like I said earlier. So then now I switch to the graph world based experiment. The problem with the graph world based experiment was the action space, because in case of Q learning, the number of action spaces are in grid world are usually very small, like just 4 or 3, right? And then there is also another approach for continuous action space, which uses policy gradient based approach. But in case of graph based approach, we do have these action spaces, but there is this chance that it will grow with the number of nodes. For example, in this case, this is a 4, this is 5th, I wrote 4. This is 5-node environment graph, right? So in case the single agent is in 0 node, there could be multiple action spaces. So in graph, I can decide that the action the agent can take when it is in 0 position is either 0 to 2 or 0 to 1. And all other action spaces I can negate or simply use a different reward or negative reward to discourage the agent from traveling that path. But in case the environment graph is fully connected, then it is possible that agent in 0 position can be connected to can take all the action spaces from 1 to 4 node. So my approach of using this graph-based Q-learning was especially the reward assignment. In previous approach in our paper, team coordination using state-state graph, we use this model of we to introduce this coordination behavior. We try to reduce the cost when the agent coordinate, and there was this. In case of here, I have added a reward. There will be a reduced cost if the agent collaborate and traverse through this path. And doing that, the overall cost of traveling from the start to a goal position will be reduced. So agents will be more likely to take that path. So in this graph-based Q-learning, instead of using the reduced state cost, age cost, I added a reward value to encourage the agent movement from this path. So there will be higher reward cost here, and there will be low reward cost here. And for the case of the other action spaces that are impossible, I added like negative reward to discourage agent from traveling. So doing this and using it as a single agent Q-learning, it will traverse from this start to this goal four node. And this is the result, but unfortunately, this result is from the 6-node environment graph. As you can see, I made the mistake and I didn't have like the immediate result for this. So I'm just taking this as a reference. So when the agent is in 0 position, it takes the action 1, means it will go to the another state 1, and then it will go to take the action 3, and then that means that it will go to the state 3. That means it takes the action 4, and then after 4 it will get to the 6, where 6 is the goal location here. So it might be a little bit messy to see that action in state space the same, but in case of graph, it's very hard to differentiate or like segregate this action space and the state space as a whole. So I had to come with a tweak to figure that out. So this is in case of the 2 agents using GST and CGST graph. In previously, I think in the first proposal presentation, I discussed briefly about this GST and CGST graph. So in case of GST graph, this single environment graph is converted into a graph where the 2 agents are also considered. For example, in this case, the agent is in 0 position, A is in 0 position, and B is also in 0 position, right? So it is possible to assume, it is possible to assume that the 2 agents can travel together, or one agent will stay and other travel and then cooperate, something like that. But they can be converted into a 2 coordinate system like this. And then this is called the JST graph, where there is 2 agents traveling, traversal map. And then if we use a CGST graph, what we can do is we can reduce the number of the nodes in the JST graph. This will reduce the number of state space as well as the number of action space for us. And then, so this is what happens in case of two agents. The action space will be pretty much like this. When the agent is in 0, 0 position, two agents are in 0, 0 position, then it is likely that they can take these three, there will be only these three possible actions they can take. Similarly, for when the agent is in like 1, 1 position, sorry, I wrote 0, 0, it's 1, 1 position, it is likely to take, it is likely to take all possible actions from here to reach that state. And then what I later did is I assign a reward, again reward for this, and I also assume this two agent problem as a single agent problem, because it was really hard to also the two agent didn't learn the coordination behavior in my previous experiment in the grid world. So it was only a ultimate approach to formulate this as a single agent Q-learning problem. And what I did was, similarly, I did for the single agent, I added the reward for those coordination A's, and then I did the same for the CJSC. And then, so this is what the optimal policy we got. There are two possible optimal policy. One is like going from 0, 0, 1, 1 to 0 to 1 to 2, 2, and another one from 0, 1, 0, 2 to 1, 2 to 2, 2, right? So for this, I have to add one more heuristic because as we know that in reinforcement learning, that if we are not very good with the reward assignment, credit assignment, there will be a lot of there will be oscillation, right? For in this case, the cost to traverse from 0, 0 to 0, 1 is pretty much same with the cost to traverse from 0, 0 to 1, 0, which means that I need to assign equal rewards for this case, right? So same with this 0, 2 to 1, 2, and then 2, 0 to 2, 1. I should also assign the same value of the reward. But when I do that, the agents start to go around the loop because it is interested to increase its reward only, ultimate reward only, right? So I had to add a trick, and I had to add reward in the goal state, and then to also make sure that it follows one path only, I had to add another reward from the last last node to the goal state. And then I think in future I can come up with some kind of random choice if there are multiple optimal path, and then when it is very closer to the goal, I can just let the agent choose one optimal path, and then it will be easy and there will be no oscillation at all. So this is the result. So it started from 0, 0 and then goes to 0, 1, 0, and then where is 1, 0? 1, 0 to 2, 0, then 2, 0 to 2, 1, and then 2, 1 to 2, 2, right? So I again did this experiment with the 4 node case. So although it seems a very simple environment graph, when we try to convert it as a joint state graph, you can see it seems relatively complex, right? And then when it is when the goal is 2 and the start position is 0, the easier path could be this, right? Because this has more cost, in previous paper.
For the sake of time, we'll probably
Yeah. Okay. So, so while I was implementing this Q-learning based, graph-based Q-learning approach, I encountered some limitations. Like for example, if I increase the number of graph size, it was getting the state space and the action space was getting very large, and then I had to define the reward matrix for this case, and then it was become very difficult for me. So also I talked about the oscillation problem. So that's what also the oscillation problem, and I had to add a heuristic during a reward assignment. And then I think for this, for the large state space and the action space problem, one solution I thought could be CJSC, because CJSC significantly reduces the state space and action spaces. Maybe I can test it in future work. I can test it for the large number of graph. Also, another thing is that Q-learning is not or doesn't always provide optimal solution. I need to train at least 1,000 episode for this, and then the chances of getting the optimal solution is like 80%, and 20% of time it is giving me like a different kind of solutions, which is not very reliable. So I try to also do some literature review to figure out if there are other approaches to improve this. So I also read the paper DQN, IQL, and then the most important papers were QMix and deep coordination graph, especially the deep coordination graph, because it used this concept of coordination graph to capture this complex behavior between agents, and it also uses deep learning approach. So in the future work, I'm planning to implement this, and I'm planning to scale this from single agent problem to a more multi-agent problem. And also test the like breaking point of this single agent problem using this CJSC graph. That's all.
I guess we have two more groups, right? You want to go next? You guys can figure out. Any questions for Nancy? Because for this reward assignment, you can just assign a very big reward for the goal, right?
Yeah, but
then that should be, removing this oscillation behavior.
I don't think so, because in this case, I want to like briefly talk. For example, it is planning to go to 2 gold, right? But 2 is itself a state, and at the same time, it is itself actions, right?
Why 2 is it's just a state? It's a joint state.
No. Yeah, it's a joint state, but in graph, while we are defining action space, it's very hard. And then when I'm in 0, 0 and I want to go to 1, 0, the only approach I can use to define the action is that I'm taking the action 1, 0, right? So which is in itself state and action.
Oh, I see.
Yeah. So what I can do is that if one has reached a goal state or very close to goal state, we can just not let the agent to take that as actions, because agents should simply take it as a goal state rather than action.
I guess
we
can talk more about this.
I got one more question. Like, if it is the same, like going from the bottom and going from the top, then why are you like always trying to go from top? Like, isn't it the same?
No, it's the same. I'm just using that as a start and a goal. I can just go from here to there.
You told me that you mentioned that going from 0, 0, 0, 2 and 2, 2, right?
Yeah.
Like taking the upwards L and then taking the downwards L has the same like rewards and same rewards and the same length. Then why is it
there is
always
oscillation?
Like, why is it always necessary to go take the upper route?
No. It is possible to take both route, but this will, if there are 2 optimal policy, the agents will oscillate, because it knows that this path will also give its high reward. This path is also give high reward. It will give equal high reward, right? So it will keep on a loop to increase its reward only, not going to the goal. So I need to introduce a heuristic. In this case, in this experiment, I introduce a heuristic here, right? Instead of introducing heuristic here, I could do it anywhere.
Introduce a penalty for time flat penalty. Every single time step you have a -1 reward.
Yeah.
To encourage you to get to the goal first, right?
Yeah.
Rather than looping around.
Yeah, I could do that, but I didn't do that.
Okay.
Yeah.
Yes, You can start sharing screen.
Stuff here.
Just you may go quickly on the parts which
Yeah. So as we talked in the last time, a project was built on traversability estimation with the real robots, and that is basically traversability estimation for the crawling. So I'll quickly go through the slides to the current state. Yeah, last time we seen with the data sample what we have collected. So that was the first work, and after that we propose to use this data to better estimate the traversability, which will be based on the current vehicle position and what it sees in front of it, and what will be the, let's say, IMU response of the vehicle if it goes there. So this is the architecture which we have proposing, or which we have managed to do right now. So this Azure Canet ROS driver, it basically publishes the depth images, RGB images, IMU data, and the point cloud. The retap map is used to provide the odometry information. It basically runs a SLAM algorithm based on the usual odometry and the IMU data, and publishes the transformation frames to the ROS. This is the ETH package. Elevation mapping is the package from the ETH library, which is robot-centric mapping of the surrounding terrain. What it does is basically it maps the underlying terrain, like a ground surface, with respect to the robot frame. So anything, let's say, from the ground, and the elevation, the difference in the elevation is mapped with the robot frame. Second thing. So we take this elevation map or grid map and use the image processing, that is taking the top view of that grid map, and create a grayscale image which maps the elevation as a value from black to white, that is 0 to 255. After taking this image, we have the odometry information from the robot. So we crop the image area which is underneath the robot. Let's say it will be a rectangle just slightly greater than the robot's own footprint, and we orient this in the robot frame. After taking this image, we pass it to the neural net to predict the roll and pitch of the robot. Yeah. Yeah, I guess. Okay. So yeah. Okay. So passing the image to the neural net, and we will predict the roll and pitch. So based on this roll value and pitch value, we can estimate if this terrain, or if this patch is good enough to travel through, or it won't be that much of challenging. So to do this, we have collected like more than 4,000 of images driving robots through the terrain on the test bed, and then processed it to train the neural net. The neural net which we are using is a convolutional neural net with 2 layers of the convolution and max pooling, and after that 3 layers of dense network. And after at the end, we are predicting the roll value and pitch value as a separate output. So after training the neural net, what we have observed is, with the less images, which we have collected like 400 images in the start, the neural net was easily remembering all those images, and the test accuracy was pretty much low. But with more and more images, the neural net is now able to predict the roll and pitch value within the range of almost 3 degrees, which is good enough to be taken as a heuristic. So this video shows some of the demonstration. So the image you see is what we are passing to the neural net, that is cropped and rotated along the robot frame. And the 3D space, what you see is one white colored dots are point cloud, and the gray area, it is the terrain map which is created by the robot-centric terrain mapping library. Sorry.
After
Yeah,
projection.
yeah, after the projection. Huh? Yeah, if you see, just a minute. Yeah, at the start, if you see here, right now it is the starting position of the robot at the start of the recording frame, and then it will move forward. Yeah.
Yeah.
So as it moves forward, it will start mapping it. You can relate it with the point cloud represented in the white, because that is direct feed from the camera.
The robot is always in the center of this.
Yeah, robot is always in the center of this, facing up, always facing up. Yeah, a bottom view or top view, whichever you say. So these are some of the sample images. The images in the upper row is elevation map, and the images in the second row, what we see is a traversability, which is a kind of a derivative of the images, which maps wherever there is a change in elevation, there will be a black patch, and white patch represents the flat surface. So these are the experimental results. The graph here shown is basically a scatter plot, which shows the true value against the prediction. So true value is on the x-axis of the roll, and prediction on the y-axis. If you see, this is pretty much with low variance. I mean, values are almost close to the prediction. This is a roll value. Yeah. So the conclusion, based on this prediction, now we are planning to use this as an input or let's say heuristic while calculating the global path to and pass it to the local planner like TV or anything to do the complete path planning algorithm. Thank you. Yeah, sure. Oh, just a minute. This one? This one? It basically is basically processing this image and creating a patches where there is a flat surface, you paint it as white, and wherever there is a change in elevation, let's say from this height to this height, so this patch will be like less traversable because there will be some change in roll value. So it is like it will create a boundary wherever there is some change in elevation, and higher the elevation change, it will be more darker.
What you guys use for your simulator?
Sorry?
For your simulator, where you were driving the robot?
No, we have collected this on a physical robot.
Oh, so this was all
Yeah, it's all on live feed.
Show him the.
Almost like 2 or 3 hours at least, because it publishes the images around 5 hertz. So almost 1 hour of recording, you get around 300 to 400 of images. So to collect the almost 4,000 images, you have to drive that much. Yeah.
You can show them this one.
Yeah. Which one? No, this is not the output of the neural net. Neural net will just output a single value of the roll, that is a float number. It will just output a single float value, that is a roll. But this will be the input to the neural net. I tried giving just the elevation map, just the traversability map, or combining both in a batch of 4. So, but just the elevation map will also work, because again, the traversability map, what you see here, it's a derivative. So neural net itself, while training, can extract it as a feature. Thank you.
We are so fast. And we are so fast. I mean, you can show them the video.
Oh, this one. Yeah, yeah, yeah.
Stop sharing.
Yeah, stop.
Hello everyone. So let's finish today's presentations. So let's quickly recap my statement of the problem. So this is the statement of the problem. So this is the overall approach overview. So we have talked in the last presentation. So I won't talk it anymore. So this is customs. So this is integer programming. Also for the Unity simulation, we already said this. Yeah. So let's talk something new. Yeah. Go to the next one. Yes. Here is the real world experiment. Here is the pipeline. So we have a robot. It has RGBD camera. So we subscribe the RGB image and the depth cam image. So for the RGB image, we will do 6 DOF pose estimation. And since we have the depth images, so we can project it to real world coordinated system. After that, we can got the real world XYZ of the detected object. So we can take this as the input for integer programming. And last, we can solve the targeted person. For the technique stack, we use Unity, ROS-P1, and Parabot. Here is a screenshot. You can see in the figure A, so that's a start thing. So we have 5 tiers, and in the right bottom we have a robot. It's a local bot. The figure B is the post estimation result. Actually, this image is taken by the robot camera. Figure C is the interesting. So you can see the robot touched the child 4. For the D and E, actually they are the reconstructed thing in Unity. So in the left, you can see there is a robot, and in figure E, you can see the water robot. Water robot also reaches the chair. Yeah, so let's see the video. Yeah, so for top left is a pipeline. So we said before. So this is a set camera. So this is not the camera on the robot. Yeah. Also, the left bottom is Unity thing. So here is a robot camera, and this is a real-time post estimation result taking the robot camera picture as input. So here you can see at this time, the OR approach already calculated the label of this chair. Actually, this chair is this chair, but the label is 5. Yeah, actually it's 4. Yeah, because the RGB camera has an effective range. Actually, this is out of its effective range, so the label is not correct. So here the objective is to let the robot move towards the chair 4. Yeah, actually it's this chair. Yeah. So let's see a video. So you can see in the red bottom, this is the pulse estimation result. Yeah. At this moment, the target is solved. You can see the chair is stable, and there is a red text. It's target. Yeah. So once the target is solved, we will issue a command to a level to a robot to let it move towards that target. Yeah. Maybe we can see again. Yeah. So at first, the robot will move forward because we need the robot to approach the target to do the pulse estimation. Yeah. But here you can see a pulse. Go back. See, there is a pulse here. It means we send a new goal to the robot. So the robot cancel the previous goal and set a new goal that is move to the target. Yes, that's all for the video. So we have one slide. Yes. Here is a limitation. So our approach relies on an accurate pulse estimate algorithm, which is input for the integer programming. Currently, we use Google MediaPipe Optron. Due to the FOV of the camera, we let the object be the center as near as possible. We didn't consider the occlusion situation, like people sitting on chairs. Yeah, that's all. Actually, that's the real time. So you see, the camera is on during the robot moves. So you always take the input, take the this image as input to do the pulse estimation. So for each image, we have the pulse estimate result. So we can, although it is not accurate, but we can also do integer programming. So you can it's shaking because it's a kind of noise. Yeah. But at this moment, you can say it is stable. It means we solved the target. Yeah. Sorry? Real animation or what? Actually, so for Unity, we can see we use ROS PY to connect the robots and the. Oh yeah. Oh, sorry, my understanding. So we use an iPad app to scan the lab and reconstruct. But for the chair model, I made it by myself. Yeah. Thanks everybody for the good presentation. So now we are talking